thank you so much all for being here. Thank you, Eric, for the nice intro. Thank you for remembering my rank within the company. I appreciate that. So I don't have t-shirts for you, but I do have stickers. I do have Flink stickers and I do have Debezium stickers. Catch me after the talk for getting some cool stickers. All right, so let's get started. And to set the scene a little bit, what I would like to talk about today is real-time data and tools for enabling you to benefit from real-time data. And why do I think this is a worthwhile thing to talk about? Well, I think the world is real-time, right? So let's say you are in the business of processing credit card transactions and you want to do some sort of fraud detection. Maybe you do some sort of analysis. Hey, this credit card is used here in Austin right now, and in 30 minutes from now, it's used over in San Francisco by supposedly by another person, right? So this seems fishy. You want to be able to detect this kind of pattern, and you want to maybe then lock down this credit card. In order to do this, you need to have a real-time data stream, and by real-time, I don't mean hard real-time, as in terms of computer sciences with a guaranteed maximum latency, but more like really, snappy, low latency, near real-time. So the world is real-time, and your data streams, they also should be real-time to enable you to implement those kinds of use cases. Because, well, as your data gets older and older, the less value it has, right? So if you do this sort of fraud detection tomorrow, well, the guy who has the credit card, they might have done all kinds of spending already, and it's just too late. So you want to have fresh data in order to react to this. Now, today, I want to talk about three particular patterns in the context of change data streaming. So this is about getting change events out of a database, something like Postgres, something like MySQL, Oracle, SQL Server, and making use of those change events. And I want to talk in particular about three different patterns, three use cases. One is the Outbox Pattern, which is about propagating data changes across microservices. I want to talk about the Strangler Fig Pattern, which allows you to move into a world of microservices coming from a monolithic context. And lastly, I want to talk about how you can go and implement audit logs. How can you enrich your change event streams with contextual metadata, like what's the business owner or business user who did this specific data change, this kind of stuff. Eric introduced me already, so I don't have to say too much. But I want to touch a little bit on, yes, for the last 5 years, I worked on Debezium, which is an open source tool for change data capture. I was the lead of that, and I guess that's what most people associate my work with. All right, so let's talk a little bit, before we get to those use cases, let's talk a little bit about some of the tools which can help us for implementing those real-time data pipelines. And the first one, well, it is Debezium. And what this is about it's about streaming changes out of a database to your consumers. And the way this works is it taps into the transaction log of your database. So all of our databases, they have a transaction log, which essentially means when transactions are coming in, writing transactions, the database will append events to this transaction log. And in that sense, it's the source of truth for our system. And what Debezium does is it gets to that transaction log, extract changes. So whenever there's an insert or an update or delete, it will capture that change and send it out to your consumers. Typically, this happens via Apache Kafka as a streaming platform. So most of the Debezium users, I would say they're also Kafka users. But as we will see in a bit, if you use something like Apache Flink, there's other means of using Debezium, and I will touch on this in a bit. Now, I could do an entire Debezium project talk, and this would be very interesting on its own right, but just to set the scene here, it's an entire open source CDC platform. So by open source, I mean it's Apache 2 license. It's not part of the Apache Foundation. It's a project which is primarily sponsored by Red Hat, but it's an Apache license project, which means you can use it as you please, you can contribute, you can fork it if you wanted to. I don't like you to, but you could. So, you have all those liberties you get with open source. And now it's an entire platform for CDC. So there is, for instance, a notion of snapshotting. This means if you set up a new CDC connector, you likely won't have the data from last year in your transaction logs. The database will discard transaction logs once it doesn't need them any longer for its own purposes, which would be typically transaction recovery or replication. And at some point, the database might figure, okay, I discard this transaction log, which means we cannot just go to the database and bootstrap the entire state. And this is where this notion of snapshotting comes in. So Debezium can scan entire tables in parallel, also while reading the transaction log to, do a backfill of the data you already have in your database. And let me also say, there's large production deployments of this. So there's people who use Debezium to stream changes out of hundreds of databases. So it's really battle proven, I would say. By the way, who uses Debezium in production? So like Eric, okay, brave soul. There's a few more. All right, very good, excellent. I would like to learn maybe after the talk what you are doing. I'm very curious about it. Cool. Right, so let's talk a little bit more about those change events. So how do they actually look like? And let me say, well, that's obviously a JSON representation, but really this is just one means of how this change event is serialized, right? It could also be serialized as ever or as protocol buffers. So the serialized format, it could be anything, but to visualize it, I obviously use something which is human readable. And that's the semantical structure of those change events. So the most interesting part is what we call those before and after parts of the change event. So they describe, in case of an update event, how did this row, this change event is about, look before and after the change. And now within those two blocks, before and after, this structure resembles your table, right? So you have a field for each column in the table you're capturing. So that's before and after. Now, of course, if this is an insert event, well, we just would have this after part because there was no old state before an insert, and vice versa. If it was a delete event, we would just have the before part and we would not have an after part. But for updates, we have both. Cool. So that's the actual data of the events themselves. And then there's some metadata, and this, for instance, tells you what kind of connector is this, what version, timestamp, when was this transaction committed, does it originate from a snapshot, all kinds of stuff like, what table this is from, and also what is the offset in the transaction log. So transaction ID, and in this case, it's a Postgres event. So we have this log sequence number, which tells you which is the position in the source transaction log where this event is coming from. So you could use this, for instance, later on for deduplication or for reasoning about the order of your events. And then there's also this operation discriminator, which tells you, okay, this is an update event, could also be like a create event, delete event, and so on. Right, and that's the semantical structure of those events. In terms of Kafka, if you are using Kafka, well, you would know, or you will know that there you also have a message key, which defines how your events are ordered, what are the ordering guarantees. And in terms of Debezium, the message key in Kafka would be the primary key of your table, which means all the change events which pertain to the same record, to the same purchase order, to the same customer, and so on, they would go into the same partition in that Kafka topic, which means you will receive the change events for the same customer, for the same purchase order in the exact correct order. So that's the message key. All right. In terms of how you could go and use Debezium, I mentioned most of the people use it via Kafka Connect, or via Kafka, I should say. And for Kafka, there's, so by the way, who's using Kafka? Wow, that's surprisingly few people. Okay, I thought like everybody would be using it. Okay, interesting. So half of you maybe. So for those who are using Kafka, they will know there's Kafka Connect. For those who don't use Kafka, I will tell you there's Kafka Connect. And Kafka Connect is a runtime and a development framework for connectors, which either take data into Kafka from an external system, which are source connectors. And now you might guess it, Debezium is essentially a set of Kafka Connect source connectors in this deployment mode. So they take data into Kafka. And then you have sync connectors, which subscribe to those topics, get those change events out of Kafka and then into an external system. So you could use those change events then to implement replication use cases, put your data into Elasticsearch to enable full text search, put your data into Snowflake, Apache Pinot if you have data warehousing use cases or analytics use cases. So you could use those change events for all those kinds of use cases. So that's Kafka Connect. Then we have what's called the embedded engine. And this means in this mode, you would use the Debezium connectors as a library within your JVM-based applications. Essentially, you just register a callback method, which will then be invoked by the embedded engine whenever there's a change event. And this is very interesting for advanced integration use cases. So for instance, for Apache Flink, there's a project called Flink CDC, which uses the Debezium embedded engine to ingest change events directly into Flink pipelines without having to go through Kafka or other streaming platforms. So that's the embedded engine. And then, well, Debezium started, very closely related to Apache Kafka, and still, as I mentioned, it is mostly used with Kafka. But then over time, people reached out to the community and they said, we like Debezium and we would like to use it, but we are maybe using AWS Kinesis or Google Cloud PubSub or Apache Pulsar, NUTS, all kinds of Pravega, all kinds of alternative data streaming platforms, which are not Kafka. And for those users, we provide Debezium Server, which essentially in your overall architecture has the same role as Kafka Connect. So it's the runtime for your connectors, but they give you connectivity and the ability to send those change events out via all those data streaming platforms other than Kafka. And the last thing I want to mention on Debezium itself, and obviously I'm biased, right, because I've been working on it for so long, but I would argue it's becoming the de facto platform or the de facto standard for CDC. So, and the reason why I'm saying this is because also other vendors, other database implementers, they hop onto the train and implement their CDC connectors using the Debezium connector framework. So the first folks to do that were the friendly folks from ScyllaDB, working on a NoSQL database, which is a wire protocol compatible with Cassandra. And they decided they want to implement their CDC connector based on Debezium, which also means now that the users of ScyllaDB and their CDC feature get the same change event format as they would get it from the other Debezium connectors for Postgres, MySQL, and so on. Which means for your consumers, or if you implement stream processing logic, you don't have to care, does this event originate from which database? You just can implement this in a unified way. And this is why I find this very interesting that folks like ScyllaDB, Yugabyte, and also Google Cloud, or Google, they decided to implement a CDC connector for Google Cloud Spanner based on the Debezium connector framework. It's even part of the Debezium project umbrella. So you now also can use, again, the Debezium format with Google Cloud Spanner if this is your kind of thing. Pretty cool. All right. Then let's talk a little bit about Apache Flink. So again, to give some context there, so Debezium is very interesting for ingesting change events out of a database. And now when I say it enables all those use cases like replication, updating your search index, updating your data warehouse, maybe I'm lying a little bit to you because it doesn't do it by itself, right? Because if you have your data in Kafka, you need to still solve the second part of this equation. How do you take the data out of Kafka? And this is where you need to think about sync connectors, which Debezium itself doesn't concern with. And also, maybe you don't want to take your data just as is, one-to-one. Maybe you want to massage it a little bit. You want to process it, you want to filter it, you want to aggregate it. Again, this isn't something which Debezium does, but this is something which Apache Flink does. And this is exactly where I think those two projects taken together are very interesting and are a very powerful platform. And again, Flink. So who's using Flink? Eric, you're using Flink? Okay, I would have been surprised if you didn't raise your hand. Okay, one brave soul is Flink. Okay, so this is my mission to change this. So next time it should be at least 2 people. 100% increase. Flink, so what is this about? It's about stateful stream processing. So this means you ingest data streams either from a database, as in the case of Debezium, but it could also be click data from your web application. It could be sensor data if you are in an IoT scenario. It ingests all those data streams, and you could have like hundreds of thousands or millions of events per second, so it's very scalable. It applies processing logic to those. So you could do simple stuff, stateless stuff like filtering, mapping, maybe like reducing your messages, like, cutting out some stuff. But it also does stateful stuff like joining operations, grouping operations, aggregation operations, windowing operations. It does all that, and it puts out those data streams into other sync systems, if you want to say that. So that's a Flink in a nutshell. And I feel I'm doing not completely justice to it because it's a very powerful, complex streaming processing solution. But that's it on a high level. And now, in terms of how you interact with Flink, so I stole this slide from my good friend Marta, which I don't believe is here, but so she did have this slide in her talk, and I just stole it because I really like it. So if you dive into Flink and you want to learn more how you use, I mean, at the bottom of it, you have like your building apps, building blocks, primitives, which let you interact with state, let you reason about timestamps, event time, all this kind of stuff. State stores, those are fundamentals. Then you have what's called the data streaming API. So that's an imperative Java API, which allows you to implement your stream processing logic in sort of like a fluent API way. We will see that in a bit later. Based on TAP, and all this, it increases the abstraction level, and it gets easier to use, but at the same time, it also becomes maybe a bit less expressive as you go up into this, during the stack. So you have what's next called the table API. This is essentially about giving you a relational representation of your data. And finally, there's what's called Flink SQL. So this allows you to apply stream processing logic, using SQL. And this means now, using SQL, this is open to use by many more people who may not necessarily be Java developers or Scala developers, but maybe they are data engineers and they are very good SQL developers. Now with Flink SQL, they can benefit from Flink, but of course there's limitations. So let's say maybe you want to reach out to an external web service to implement your streaming job. Well, you couldn't do this using Flink SQL, right? So you would have to use one of the lower level APIs. All right, so let's talk a little bit about taking those two things together, Debezium for CDC and Apache Flink. Now, in the simplest case, you would just use, or you could use it for a pipeline like this, right, where you have a Flink CDC connector. By the way, I should say Flink CDC. It's a side project or a project from the Flink ecosystem, which deals with integrating CDC connectors like Debezium into Flink. So we could have a Flink CDC connector, we could have a GDBC sync connector, and we would just implement a very basic data propagation pipeline, I guess you could call it. Very often, that's not enough, right? You want to do more interesting things with that. Maybe you want to filter your data. So common use case is data formats. Maybe you want to, adjust them to UTC or just have a specific time format. So you could use that. Maybe you want to mask sensitive data. Maybe you have something which you don't want to expose. So you could use those stateless filter map operators for those kinds of operations. Encryption, another nice use case. So that's stateless transformations. You could, similarly, you could implement routing. So maybe based on the context, on the content of an event, you could route it to different things. So maybe you have a stream of purchase order change that's coming in, and now depending on the type of the purchase order, you want to send it to different data stores on the sync side. So maybe, B2B orders should go there, B2C orders should go there. So that's routing. And of course, it's not, as I mentioned, limited to JDBC. So there's a very rich ecosystem of connectors on the source and on the sync side. So you have connectivity with Elasticsearch, MongoDB, Pinot, Snowflake, S3, and so on. All that via Apache Flink. All that is stateless so far. And I guess that also, enrichment also would be still stateless. So, but maybe you have your change events and they are not like fully self-descriptive. So maybe they contain some sort of IDs which you want to resolve into like a proper business identifier or something like that. And this information is stored in an external system. So you could implement in some sort of enrichment use case where you go to this external system and resolve those IDs. So let's move on a little bit to stateful operations. So you could join your stuff. So maybe, and for folks who were in my demo yesterday, they saw that. So maybe you have an event stream via Kafka. So maybe a purchase order is coming in via Kafka, and you want to, again, add some reference data to this, which you receive via Flink CDC. So you could implement a sort of joining use case. Flink would take care of keeping track of the state, making this failure tolerant, and so on, and you could send it out to your consumers. All right, so that's on a high level, a few things which you can do, on a rather abstract level, I guess, which you can do by combining Debezium and CDC with Flink. Now let's talk a little bit about some more specific use cases, and they are particularly in the context of microservices. So that's what I want to focus on a little bit. So let's talk a little bit about the Outbox pattern and taking data or exchanging data between different microservices. So again, more specific use case now in the context of microservices. Now, if you think about microservices, the situation there is you want to isolate the parts of your domain, right? You want to make them that they are mostly self-independent. In particular, you don't want your services to share databases. They each should keep their own state, and you want to reduce the amount of interactions between your services. But still, I would say, they don't exist in isolation. As hard as you try, your service will need to interact. So let's say you have a service which receives purchase orders. This needs to somehow notify a service which builds your shipments and which sends out the shipments to your customers. So these services, they need to interact with each other. And now the challenge there is, well, as those services themselves are not stateless, what typically needs to be done is each service needs to update its own local database. So this order service needs to, persist this purchase order. And then you also want to send out this message to your other services. And on the surface, you might think, okay, let me just do this. Let me, commit a transaction to my database, and then let me send out an event to the other services, maybe via Kafka. And the problem there is that those two resources, a database and Kafka, they cannot participate in a shared transaction. So, you don't have XA semantics with Apache Kafka. This means those two things, they are not guaranteed to happen atomically. What could happen is you commit your database transaction, but then you fail to send out this event to the other services. Maybe a network split or whatever went wrong, your service crashes, and now your overall data state is inconsistent. And this is, of course, something you want to avoid. Or maybe even worse, you send out the message to the shipment service via Kafka, but then for whatever reason you fail to commit your own local transaction, which then maybe means you have initiated a shipment, but you don't have track of that order in your own database. Obviously not a good situation. So how can we go and solve this? And so exactly, that's the situation I mentioned, right? So, doing this kind of stuff, dual writes, trying to apply changes to multiple resources which don't share transaction guarantees, it's error prone and you should avoid it. Now, if you think about it, CDC, change data capture, can help you with us, right? Because what we could do is we could capture the changes from our tables, maybe our purchase order table, and send those change events out to our consumers. And that's so then we don't have this dual write aspect, because when we just update our database and the CDC process would happen afterwards. So we avoid the consistency issue, but we also are at the risk of exposing our internal data schema to the outside world. Because, well, if we capture changes to the order table or to the order line table, well, if we do changes to those tables, maybe we change column names or we change types, we add columns. All those changes are impacting our downstream services. And this is something which we don't really want, right? We want to shield our internal model from any external consumers. And this is exactly where this Outbox pattern helps us. So the idea there is, if this order service receives a transaction, it updates its own internal tables. So it would go and insert data into the order table, order line table, and at the same time, it would insert an event into another table, which is called the Outbox table. And now this Outbox table, this is essentially our messaging channel to the outside world. And all this happens in a single transaction, so we don't have this dual write problem, right? So either this transaction gets committed, so we apply our data changes and we insert the Outbox event, or we roll back this transaction so nothing gets persisted. So this happens atomically. And now we would use Debezium to capture the inserts into this Outbox table, and it only would ever be inserts because, well, we never wanted to update events after we have produced them. So we would capture the inserts from this Outbox table, and then we would use those Outbox events and send them to our consumers. How could this Outbox table look like? Well, here I like to think about it in terms of domain-driven design. So, if you are familiar with that, there you have the notion of an aggregate root, something like a purchase order, something like a customer, and you could implement this based on the semantics of the of domain-driven design, which means in this Outbox table you would have stuff like, what's the aggregate type? So is this Outbox event about purchase orders? Is it about customers? And so on. which then, for instance, we could use to, derive the name of the Kafka topic from that aggregate type. So we could send events to different topics per aggregate type. We have something like the aggregate ID. So that's the primary key of our data, which we will use for ordering semantics. Again, this will inform the Kafka message key, essentially. We could have something like an event type, which is about, like a fine-grained type of event. If this is an order event, is it like order created, order line changed, and so on. And finally, we have this payload field. And this is now our message contract with the outside world. So this is, very, say, how does this event look like? And very importantly, and for the sake of the example, here I use JSON, but again, it could be Avro or it could be anything. But most importantly, this contract which we use in this payload column, this is independent from the internal table structure, and these two things can evolve independently. So, for instance, we could rename columns in our internal table model without changing the name in the JSON message which we send. So we can evolve those things separately, and in particular, we can evolve the Outbox message contract with backwards compatibility in mind. Right. So now I wanted to just briefly mention how does this relate to Flink? And there's an interesting use case. There are an interesting implementation alternative of this Outbox pattern, and this is like this. So here I mentioned, okay, this is an Outbox table. So we insert events into a table. But if we use Postgres in particular, we could use a nice trick there. We have a function which is called PG logical emit message, and this allows us to just send events into the transaction log of the database. So they will never show up in any table in Postgres. They will just be appended to a transaction log, which is pretty much what we want, right? We don't really need a table with that. We don't want to query those Outbox events in our database itself. We just use this mechanism to get out those events by the transaction log. And this is exactly where those logical decoding messages help us. So we can insert arbitrary content into the transaction log. There's a discriminator, Outbox messages in this case, and again, my payload. So we can use this with Postgres. And what I then can do with Flink, well, I can ingest the changes from there. And this is where, again, this project Flink CDC comes into the picture, because now here, looking at this Java data streaming API in Flink, what I get from Flink CDC is a Postgres SQL source, which I can use, to connect to my host, connect to my database, give my credentials, and so on. And then I have what's called a source function in terms of the data stream API. And this source function produces essentially events, in this case, coming from this Postgres database. And by the way, this Postgres SQL source, that's exactly built on top of this embedded engine, which I mentioned earlier. Now I have the source function, and then, I can use the data streaming API to implement a very basic pipeline where I would also set up a Kafka sync, specifying my Bootstrap server, all this kind of stuff. I put those things together, and well, I built up this pipeline, and in particular, I filter also those events, because here I'm just interested in those events which have this operation type M. So it's a logical decoding message, which are exactly those events which we inserted to the transaction log. And I can now ingest those events. Now, there's one thing which I also need to do. I need to, apply some sort of routing logic to make sense out of those domain-driven design semantics which I mentioned. And this is what we see here. So that's a custom serializer. So if I go back, you see it's, this is used here. So we just apply this to every event which comes into the stream. And there, essentially, we just say we want to customize how this Kafka message which we send out, how this should look like. So in this case, we do exactly what I mentioned before. We use the aggregate type as the topic name. We use the aggregate ID as the Kafka message key. We propagate the payload as our Kafka message value. And then we also insert a Kafka message header with the unique event ID, which consumers, for instance, could use for deduplication. I know it's quite a bit of code, and at the end I have a link where you can, download all the example from GitHub, and you can try it out yourself. All right, so that's the Outbox pattern. Let's talk a little bit about another situation where you are not yet in a world of microservices, but you want to move there. And this is where this Strangler Fig pattern helps us. And by the way, if you wonder why it's named that way, well, the term was coined by Martin Fowler, and apparently he, became aware of those strangler fig plants which grow around an old tree, strangle it until it dies off, and this is exactly what reminded him apparently of the scenario where you have a monolith which you want to, move to microservices step by step. Why do we want to do this? Well, if we want to avoid big bang migrations, right? So maybe we have a large monolith, we want to split it up into 10 microservices, and we don't want to do all this all at once because it might be too risky for us to do it. Instead, we want to, do things. We want to take things step by step and extract one service or maybe functionality of one service one step at a time. Maybe pause and all this kind of stuff. And this is what this pattern is about. So. And this is how it looks like. So let's say we have, a legacy application, maybe Java 6, a very old version of Spring, and this is our monolithic application. And now I would argue, yes, it's a deployment monolith, but most of the times you still have some sort of structure there, right? I mean, I've never seen really this case where everything talks to everything. It's like a huge big ball of mud. Maybe I've been happy, I don't know. But usually I feel there is a structure of components which you can find in monolith. Now let's say we want to take one of the components from this monolith and extract it into a new service. First step would be to add a routing component in front of this. So something like Nginx, Envoy, whatever proxy you want to do, HA proxy. You put this in front, so you are able to route requests, different kinds of requests to different targets there. So we would, we put this in front, and then we would add and start and extract a new service. So maybe we want to take this owner's component from this monolith and move this into a new service. Maybe this also uses another database, MongoDB. So we would use Debezium to set up a change event flow, because for now we would still keep all the write access to this application, to the monolith, but then we would propagate the changes to the owner's domain over to this MongoDB instance. We would have a sink which applies the changes there. And now our routing component would make sure that maybe initially just some reads are served by a new service. And here, for the sake of the example, again, I've used a different stack, Quarkus, new Java version, and maybe we just have a single read view which we have in this new service, and we would use the proxy to route the reads to that service. To route some reads to that new service, and it would have the data by means of setting up the CDC stream. Now we could, keep moving forward with this migration, and we could also say at some point maybe everything which pertains to the owner's domain, all this is now owned by this new microservice. So this is entirely gone from the monolith, meaning also all the writes will now be routed to the new microservice. So that would be good. But the challenge there is, well, maybe you have other parts in the domain of the monolith which also need to have access to owner's data. For, I don't know, maybe for doing some reads in the other components, or for resolving some references. And so now what you could do is you could set up a CDC flow in the other direction, which propagates owner changes back to the monolith, so you could resolve those references. What you just should be careful of, for each part of your domain, like a component or maybe even a table, you should always have one component who is in charge. So you shouldn't have writes for owners on both sides, because then you would end up propagating the same changes probably forth and back in an infinite loop. So that's what you not want to do. So that's how you could go about such a migration. Again, there's a demo repo where you can find out more about this and you can play with that. But let me touch a little bit on some of the challenges. Again, we have this question, so don't we leak information? Because, well, if you just capture our tables as they are, maybe we don't want to impact our new microservices with all the minutiae of the old model. Maybe we had limitations in terms of how long can column names be there, or we used some awkward data types. We don't want to expose all those oddities to our new microservices. So that's the question. How can we isolate those things? And maybe we also want to think about aggregating data. Maybe in particular, if you use a document store like MongoDB, instead of having data in multiple tables, maybe we want to join it and aggregate it and put it into a single document in such a document store. And this is again where Flink would help us. So let's go there. So we could have a Flink application, which, for instance, does filtering, does sanitization of column names, massaging data types, all this kind of stuff, and also joining. And this is, this is an example how this could look like. So by default, if we had an owners table and a pets table, we would have this data on multiple change streams. But maybe this is how we would like to have this data in MongoDB in a single document. So we want to join the data from those topics, owners and pets, and we want to aggregate it per customer, per owner, and put it into a single document. And to do this, well, we could again use Flink and Flink CDC. And now I mentioned there's different APIs in Flink for implementing logic. So I showed you the data streaming API. I also want to show you the Flink SQL API, or yeah, the Flink SQL. And the way you would interact there as well with SQL. So you would say, something like create table, which essentially represents a source stream. So you say, this is of the connector type MySQL CDC. Again, you give your credentials. And this gives you now a stream or a representation of this data in Flink. And you could then use Flink SQL to reason about multiple of those streams. So here, don't be too intimidated. What I'm just doing there is essentially I just join multiple of those tables, and then I use a few custom functions to essentially aggregate those data per owner and put it out into another table via this insert into statement at the top. So just to give you intuition, you can implement those use cases also in terms of SQL in a purely declarative fashion. All right. So by the way, how much time do I have left? 7 minutes. Okay, that's pretty cool. All right, cool. So then let me talk about one more use case, and this is building audit logs. So the motivation there is, well, you have those change event streams, and you saw those change events with the before and the after part, and some kind of technical metadata, like what's my table, what's my connector, timestamps, transaction ID, and so on. But at the same time, this stream of change events is lacking some more higher level business oriented metadata. So typically you want to have something like, what's the business user who did a particular change? Maybe you want to have like a use case identifier or like client device information, client IP, this kind of stuff. And you don't store this sort of information in your business tables, right? So the change events which Debezium or any CDC tool can get out of your tables, they would lack this sort of higher level business oriented metadata. And again, we can use stream processing to enrich our change events with this metadata. Now the question is, where is this metadata coming from? And again, we could use, we could insert metadata into another table. We could then join those table streams. But here, and I guess by now you realize I'm a fan of Postgres and I'm a fan of logical decoding. Again, we can use this function PG logical emit message to insert this metadata at the beginning of each transaction. So in this case, we say, and by the way, this true parameter says that's a transactional message. So this means this only gets written out if this transaction gets committed. Otherwise, it would not show up in the log. We say it's of a specific type, audit metadata. And again, our payload here, that's the metadata which we want to put into our change events. And we do this once at the beginning of each transaction. So there we would use, we add our business user and all this kind of stuff. So that's a specific operation which we do from our application. And then we do this enrichment part. And so this is how it could look like. So, if I have a transaction flow, I do my begin. At the very first thing I do for each transaction is I call this function to provide my custom metadata. Then I do whatever data changes I want to do. I do an insert into customers, addresses, and so on. And then I commit it. So that's my raw change event stream. And what I would like to do is I would like to take this metadata and put it into each of my change events. And coming back to this data streaming API, there I could use what's called this flat map operator. So this essentially allows me for each event which comes in to emit 0 up to n events. So I could say I want to discard an event, I want to ingest one event and emit one event, or I can emit multiple events. And I use this flat map operator to implement essentially a logic which goes like that. So if my event which comes in is such an ordered metadata event, which I recognize because it has this op type M and it's of the type, the prefix is ordered, then I take this metadata and put it into some state store. So Flink allows me to keep state. So I put it there, and then when another change event comes in, which isn't such a metadata event, then I will go to my state store. I will look up, is this the same transaction still? And if it is, I take the metadata from the state store and put it into my change event. So that's the high-level intuition of this logic. And again, there, I have an example for all of this on GitHub. All right, and that's pretty much all what I wanted to show you. I hope I could make the case. Well, yes, so this notion, coming back to the beginning, this notion of real-time data, of having fresh data, this is becoming more and more critical. It allows you to just react to your data with a very low latency. And there's all kinds of use cases. So for instance, if you do dashboarding, maybe with Apache Pinot, you want to have fresh metadata on such a dashboard, right? Or data on such a dashboard. You don't want to have old data. So you want to have fresh data. And in the context of databases and ingesting changes out of those databases, Debezium is a very powerful open source tool which gives you this. Just to give you one example, I know of users who do CDC pipelines from Debezium, MySQL, a cluster of MySQL databases, into Google BigQuery for their analytics purposes, and they have an end-to-end latency of less than 2 seconds. So within less than 2 seconds after something has changed in their operational database, they have this data in their analytics platform, so they can run, well, I would say real-time analytics. Combining this with Flink, takes it to the next level, right? So we can do all those kinds of things like filtering, massaging our data, joining it, or windowing. I mean, I didn't speak about windowing, but we can do stateful stream processing in all kinds of shapes and forms using Flink upon those Debezium events. And lastly, if you want to learn more, so I just wrote an article for infoq.com, which is called The Wonders of Postgres Logical Decoding Messages, where you can learn a little bit more about how you can go about those PG logical emit function, PG logical emit message function, and how you can use this, how you can process those changes with Flink. So you can find this on InfoQ, and you also can find on the Decodable GitHub organization, you can find the source code of that. And with that, I'm done. You can hit me up on Twitter. You can hit me up via email. And of course, you also can come, I should say that, you can come by our booth, you can grab some stickers, you can ask questions to, well, Eric, are you there? I don't know, but maybe, our staff at the booth. We can talk about Flink, Debezium, and everything in between. Thank you so much.